right, welcome everyone. Our next speaker built his last startup entirely in Gleam, but today I'll be speaking on the EYG programming language. Please welcome Peter Saxton. Take it away.
All right. Hey, thanks for having me. Sorry I couldn't be there. Yeah, I'm watching the Discord if people have questions, and I'm kind of happy to try and fill them as we go through. So if people want to drop them there, more than welcome to. So I'm going to talk about removing fragility from software with the EYG programming language, which is, a large claim, and we'll see how much I can back it up as we go along. So I'm Peter Saxton. I'm crowd hailer on the internet. I've done a bunch of stuff with Elixir, Gleam, and EYG now, and it's all general experiments to try and make kind of better software for some measure of better. That's kind of the key thing. So let's start with some definitions. This is a good tradition. So what is fragility? So how susceptible is something to damage or breaking? And both of those, particularly breaking, are vague terms that we're going to have to dive into a little as we go along. So why do programs break? We're going to leave the question open at the moment. You probably have an intuition, and let's do the little bit of AI. So AI is good for average knowledge. I think that's probably what it's best at. I really enjoyed this answer. It was spot on. No context at all. As many assumptions as you want. Tell me why your program is no longer working. Oh, it's probably NPM, right? ChatGPT, yeah, you've nailed it. You've got dependencies straight at the top. Other things that we come up with, this is just a list. This is my first query. No sort of massaging at all. Bad state, bad timestamps from the outside world, race condition. This is probably the one we will touch the least along the way. A few more of them. Fix the bug was hiding a bigger one. Okay, maybe we won't deal with that. But yeah, the wrong environment. A lot of this stuff is kind of the outside world and the system. There's not a lot here of your program is broken. That's not something which shows up. Again, we've got external services. You're probably calling over an API. And this final one I like. It's actually working. So it's a feature, not a bug, which they've managed to obviously bear that in mind, that maybe it's not broken, just change your expectations. Okay, so what helps with making software less fragile? Well, there's a lot of approaches, because obviously we never want our software to be fragile. So type systems are what we're going to talk about today, but I thought it was fair to mention that we have formal proofs, we have simulation testing. We've tried to change how we deal with programs. So immutability, there's less possibility for mutability bugs obviously come in. We have containers where we have Docker. We also have tools like Nix where we try to tie down the environment, because the environment changing around our program is a large part of what makes our programs flaky. Okay, so moving on to the next one. I can see mentioned in the Discord, it's good. But yeah, so for this talk, for the time being, we're going to really focus on not crashing. So I really like this slide. I like how quickly you can do this. Okay, so here we've got the add function. We add 2 and 3 together and we get 7. Okay, 7 is not the answer. So this is wrong. And then we've got subtract 2 and 3 and we get uncaught reference error, foo is not defined. So I'm going to make the argument, and it's kind of an assertion that we're just going to roll with today, that the second function is more broken than the first one, in that a non-technical person would be able to understand the first thing. They're like, okay, you've added the numbers in the wrong order. Maybe there's a incorrect mathematical function. Whereas the second one is wrong in a way that drags all of kind of your computer knowledge into it. And I think, dealing with crashes, undefined is not a function. There's a lot of most languages have their version of kind of a nil pointer, or out of bounds, or stack overflows and stuff like this. And they're harder to debug because your knowledge is not related to the business, or at least, well, maybe they're easier to debug if you've got good stack tracing. But I want to kind of separate these two things. And for the moment, we're going to try and get rid of crashing. Okay, so this is a program going out of bounds, not doing what it said it did. So where do crashes come from? So to me, this is one of these things I find quite fascinating. Crashes are weird. I spend a long time, we program and we think we are, to some degree engineers or mathematicians, or we're building on a rich history of for example, lambda calculus. I mean, this is called LambdaConf. Okay, we're leaning into the fact that we've started with lambda calculus, we're mathematicians, and we've logicked our way to this richer sort of world that we're in now. Lambda calculus cannot crash. So lambda calculus may not terminate. This is the halting problem. So this expression here will never reduce to a smallest term. So this is a function where you kind of call the argument with itself, and to call the argument, it just keeps calling around and around. But somewhere in going from lambda calculus, the languages we have today, we added the ability to crash. Maybe not deliberately, but it was added as we extended our use of computers to more places. And so what we kind of get is, this is kind of the message that we're going to double down on and triple down through the course of things is, here we have a Python program, a very simple Python program, and EOF when reading a line. So this is crashed. And what's crashed here is, this is the error you would get if standard in, which you're trying to read from, is not available. So the program is sensible, perfectly sensible program, but the outside world is not set up in the right way. So the program depends on the outside world, and the outside world has let it down. That's the way I like to kind of think about these kind of crashes. Okay. So what is EYG? So EYG is a way to write programs that never crash. And we're going to be very careful about our definition of crash. And the other part of EYG, which we will touch on today, is that they run anywhere. Okay. And the way I go about this is, to some degree, we try and make invalid states unrepresentable. So EYG, the basics, it's statically typed, it's structurally typed. The type inference is sound, so that if it type checks, it's guaranteed to have an answer of the type that you were expecting, unless it runs forever, so we can't solve the halting problem. We have algebraic effects, which we dive into. We have closure serialization, which we dive into. And then we have a strongly typed REPL, inline references, and a minimal AST. Those last three we will talk about less, but they're all part of kind of the feature set I've lined up with this idea of making programs that are not fragile. Okay, so EYG, it's quite weird. We have a structural editor. You can't type EYG. It has no parser. So here is the editor in a slide. So if we want to set x to a number, so we say the number 10. Okay, we have to press E. I mean, I can't show you what I'm pressing to get an expression. So I didn't type let, and now we have a program that returns x. If I press V, we get the variables in scope. We can see that x is in scope and that x has the type of an integer. If we run that and its expression, we get the return value of 10. In a reference, there's the standard library. Okay, get a field of this. So we say list. We get another field. We say map. This takes 2 arguments. So we fold over it. We're going to get a list of 2 numbers here. Let's make the first number 1. Let's make the second number, well, we can make the second number x. And then we might want to add on this. So let's put a variable above. We'll call this integer. We'll make that a destructure. We'll pull this off the standard library. So we're going to list.map. Let's see how good this is. Essentially live coding, but we get slightly less errors here. So if I do the integer, okay, type error, but because we've got the whole module, we get the field add. 2 arguments, but we only need 1. Everything's curried, which is why I like showing this example. So integer add 1. Well, let's, add 1. Submit this. Okay, we can now run the program. We get the list of 2 and 11. Okay, so that's compound data structures, modules, literals. The other thing we have are records and variants. So records are extensible. So if we do a function which takes a user and we want to get the field name off it, okay, we need to label, call this something. So we're going to call this the foo function because I've run out of suggestions. We can pull the foo function in. It takes the name of any type. So 0s are unbound. 1 is the polymorphic in the rest of the record, and we'll return whatever's on the name field. We're not bound this to being a string in any way. So if we call foo, call it with a record. If we press R, the editor knows that that type is what's going on here. So if I'm going to call this, I'm going to be Bob. But we could add another field. So on the side here, we have ways to click through adding stuff. So we can have age, number 100. We run this. we get the name Bob off here. And kind of to finish off, we'll just do a quick one with the enums. So if we have a built-in equal, we give a number 10. We have another 10, so these are going to be equal. So the type of this is a true or a false. It's an extensible enum, so it's not a Boolean type. It is literally the union of a tagged thing of true and a tagged thing of false. So if I want to match on it, just pressing M will give me the true or false options. So to prove that it's just a union and not like a Boolean type, if we undo this, assign this to a value of result, and we run this. Now, if we look in the environment, the result type is available. Sorry, the result variable is available, but its type is just true. Okay. So this is kind of the important of it being extensible. So both the records are extensible in the way you can have extra fields, and variants are extensible in that you can both extend and shrink the variant type. So if I now try to do a match on this result, we just match on it being the true type. Okay. So yeah, so that's the kind of the basics of EYG. All right, moving on. So what is eat your greens? So beyond diet, eat your greens can symbolize doing things that are good for you, even if they're not immediately like enjoyable or easy. And this was a philosophy I had when kind of building the language. Was I knew I wanted more from my compiler, from my tools, from my type system. But like there was a certain amount of pain in constraining yourself so that you could get the things you wanted. Like you can't write lambda calculus, you have to extend things usefully. But what's the minimum amount you can extend things? Like what is the most kind of good for you diet in a programming language? It's kind of the opposite of the express yourself version of like, I want power and all the tools. Like what's the least number of tools? I can get the job done. If I follow this really restricted diet in my programming language, like how good can it be? Like what can be built on top of it? So the features of EYG, all of these I think are slightly vegetables, like algebraic effects, which we're going to talk about first, structural typing, and hash dependencies. So effects, what can they do? Pardon me. All right. So algebraic effects are a specific way of doing effects. I think effects are fair to say are such a large term that does your program an effect in the outside world? Fine. Algebraic effects say that there's a sound algebra, a way to represent them mathematically, and in doing so, we can start adding typing to them again. So algebraic effects, they cover input-output. They also cover all non-determinism, i.e. a single lambda calculus can't represent randomness. Time has to be pulled from the outside world, exceptions, concurrency, mutability, all the issues that were mentioned in the GPT answers right at the beginning. So using effects, what can they do? So the effect interface is universal, and I'm just going to kind of show them first. So for example, I talked about time. So if we want to get the time, so pressing P gives me all the effects that are available in this environment. We have a now effect, which takes a type of an empty record and returns a string. So if I go here, I give it an empty record, I run now, we can see it's 9:43 UTC. Effects are also, they're useful in that they can define an environment you're in, but I think they can define more than you might just expect working from a normal program environment. A normal program environment, you expect standard in, you expect the file system, so on and so forth. But this shell knows that it's in a web, so it has a few effects which are slightly web specific. So we have the geolocation, and we also have kind of my favorite one for just showing off here, we have download. So download is an effect which takes a record, which has a name and a content. So if we go through this, if we give this the name hello.txt, and this has to be a binary value, so we need to call string to binary. If we call this with, okay, so it's going to go hello world, we submit that. Now, if we run this program, we get, sorry, download started. I think I have to leave full screen mode. Are we going to do this? Are we going to try it? Yeah, we are. Yeah, here we go. So we've in this effect in the browser has shown us hello world.txt was the effect of this program, and it returned an OK result. And when we run effects, the programs have a record of all the effects that happened during that execution. So let's full screen this again. It's full screened to the other page, obviously. Can you not just stay on this one? Full screen. Right. 2 seconds. This time we will full screen here. Yeah, we do. Great. Okay, onwards. So algebraic effects. They represent every interaction with the real world, and they bring it into the type system. So a function being pure means that it has no effect. So an add function takes an integer, returns an integer. Well, it takes two integers, pardon me, and returns an integer. The alert function has an effect I call alert. That was a sort of browser one. There's a browser primitive to do that. The interesting thing about effects here to note is that functions can be polymorphic over the effects that they have. So this map function takes a list. So here we have the list of zeros. So zeros are a type variable. It could be anything. And we have a function here where this 0 and this angle brackets 2 are the argument. And it goes to a 1. So the 0 and the 1 are the input type and the return type. So the element type is 0. So we have a function with a list of elements, and we have a function that takes that list, that is one of those elements. It returns a 1, which is just another unbound variable, and we're going to get back a list of 1s. Now, inside these angle brackets here, we have this other unbound variable 2, and it matches here. And in this case, it's saying that the function that we pass in, the mapping function, will raise or could raise some effects. But if it does raise some effects, then the map function itself must also raise that. So if you iterated through a list of numbers with a function that was to alert, then it would alert, when calling that, it would alert for every item in the list. Okay, I think we got an example of some of these going on a bit further. All right, so let's start with some of the stuff here. So we've got a couple of things going on with effects. Putting stuff in the type system means that an effect that doesn't exist, so I don't know, we can have shoot lasers. If we try to do this, oops, let's do a record. Missing row shoot lasers. Like shoot lasers is not in the environment that we have here. I suppose another interesting one is, file read is also not available in a browser. But we can, if we don't use this now, if we make a function like this, and we make this function, we're going to call this one f, and we run it, and we look at our variables in scope, we can create a function with an effect we don't know yet. So we're not using this. File read is in the signature of this function, but it's fine to create it as long as we don't need that effect yet because we've not called it. I also kind of want to demonstrate that they're composable. So let's not use an effect that, well, it doesn't matter. We can use an effect that doesn't work. So if we make another effect, function g, which takes nothing at all, we're going to perform alert with hi. Okay, we build this. We can see that we've got, pardon me, two variables in scope, each with their own effect. Nothing happening with them. But then if we make another function h, function underneath, we'll say call f, call it with an empty record. We'll go along, we'll call g with an empty record. If we run this, we can then look at our environment again. So we've now got h. So h has these two effects, file read and alert. And I think in practice, I picked one we could run, but never mind. So if we bring up h and we call it, we immediately get the error again. So everything's bubbled up through. You can't use h in this context because h relies on an effect, which is not available in this context. And that missing effect is file.read. So this is kind of one of the key points about algebraic effects is they bring this previously unspecified part of how our program was working into our programs. So there we go. So effects become the only interface in a program to the outside world in EYG. Other languages which do this, they leave a debug statement or, you can access standard in or standard out. It says no, effects are the only way you can talk to the packed developing within them. So here we have a function called tweet. So tweet is something that could rely on the effect fetch. Okay, so you put the text of what you want to send, and it has the type fetch. So this is an HTTP fetch. But in doing so, that means in your program, you would have to get hold of a token and know which API to call. Pardon me. At the other end of the extreme, you could have a tweet function which had the explicit effect twitter.tweet. And in this case, you could imagine that the program does nothing but just call this function, this effect. It performs this effect with the message of what you wanted to tweet. But if you did that, then the platform would be responsible for providing such an effect. So we can see here that the range is, if you have a very explicit effect, then the platform has to create lots of effects to be useful. I mean, if you have a very generic effect, then you put a lot more emphasis on the EYG program to call them correctly. And here I think we have an interesting middle ground, which is what I'm kind of building at the moment, where actually this shouldn't say tweet, it should say Twitter, which is I have an effect where I can call the Twitter API. The platform knows where the API lives and will maintain an authentication token, so my EYG program doesn't have to, but all the knowledge about what endpoints are available are inside the EYG program, which means the platform only has to know that Twitter exists. It doesn't have to know the Twitter API. I think that's an interesting balance, but I've explored all of these. And as I mentioned, it's kind of a design space that, you could choose any of them with EYG programs and EYG runtimes. One of the downsides of EYG is that it's slow, or it can be slow. Like, it hides everything about the machine. There's no way to address certain bits of memory or to do really efficient algorithms. But this effect interface allows you to solve for basically any slowness by taking it down to the runtime. So if you have a highly functional language, if you have a highly pure program in EYG, or you use EYG because you want a lot of the guarantees, but then you find you need to look at a load of PNGs and recognize if they have cats in them. Well, you can make an effect, which is called isPNG, image of a cat, that takes a binary. Your program can now only run on a platform that has this effect in it, but the type system will check this for you. So I think this is quite a nice way of kind of leveling stuff out from kind of the glue or prototype or quickly iterating code into the kind of more serious base code. I know I'm kind of, EYG is new and I'm exploring exactly the interface of the effects, but this is kind of useful. And it's kind of related to this problem, which, so I don't know how many of you are kind of in the Erlang or Beam ecosystem, but this year, Erlang is getting kind of TTY support in the terminal. So a lot of people come to Erlang and they've kind of wanted to write CLI tools, and you've not been able to do stuff with a TUI. But Erlang's almost 40 years old. I just assume that it's there, is what this guy is saying. But if you had an effect platform, then all of this would be immediately visible to you. Like, if you wrote a program that relied on TTY being available from the platform, it would immediately type check and go, that's not available here. And you go, oh, cool. But it allows you to subset your platform. So if you have a piece of code that doesn't need a file system, it's incredibly easy to check this up front. Whereas if you just have a Python program, you don't know whether that can or cannot run on a read-only file system. Okay, so effects are a uniform interface. They're a singular approach for mocking, and they become a basic permission system. So I don't need to lean into this too much, but it is to about the same degree that when you install an app, the app asks if it can access your location, if it can access your contacts, if it can access your file system. All of this would be improvable in your programs as well. So when you install them by default, if you get a piece of code and it says it's going to be an API client, yeah, you should be confused if it reads the file system. Okay, so we can handle, so I say there's a universal interface. This one I'll do reasonably sort of short. But yeah, if we make a function which we're going to call exec, and this is just going to have a list of, say, 2 flip effects. So we run this. We have a flip. These are random. We need to call this something. Yes. So actually, this should be an empty argument. We're just throwing it away. And the whole thing should be called exec. So we run this. So bring it up. Exec uses the flip effect. It returns a list. So if we call it, we get a true and a false. Okay. But we can also, I mentioned, use this kind of universal handling interface. So if we handle it and we say handle the flip effect. So this is a function that, well, this is actually a kind of program literal, which is taking 2 functions as arguments. So here we have this value and resume, which is what to do when an effect is called. And then here we have the function we want to call it with. So this we're going to delete, and this is going to be exec. Oh, no. Yes. Okay. We had, for some reason, this issue earlier, but we'll rebuild that. So we've got exec. We'll click handle flip. And we will delete that. We will put exec in. And we'll say what we want to do is when it's the flip value occurs. So we're performing the flip effect with the empty record. So this value is meaningless. This value is just going to be that empty record. But resume is the rest of the program. So what we can do is we can call resume, and we can call it with something. We could call it with true, we could call it with false, but we could also call it with something unrelated. So we could call it with maybe. Okay, we're going to always return maybe. We run this program now. Okay, this exec function performing the flip effect in this context, we get maybe, maybe. Okay, onwards. So how do they run? So how much time have we got? So, okay. I kind of talked through this before. So this is a function. We have functions, they're inputs and outputs. When, these are the things that I was confused, they crash. Functions compose and functions can be values. We're at LambdaConf, so we probably won't drill down at that point too much. Functions without effects, they have side effects and they have side causes. So here we go. This random function cannot be a function in the mathematical sense unless we use the xkcd joke and it always returns a 4. The print function takes a string and returns unit, but it always returns unit. And without side effects, it doesn't do anything useful. Okay, so here we go. Good old xkcd reference. Time to enjoy that if you've not seen. But yeah, okay, so side effects depend on the whole world, right? That you reach out, okay? There's nothing about what we're talking about in the program which constrains that. So we're going to need to take a quick aside for continuations. So continuations, again, maybe this is a functional conference, maybe you've come across these, but the kind of way to explain these is a normal function, you have inputs and you have outputs. The output then goes on to the rest of your program. The idea of something which takes a continuation, here we have this add k for continuation, is everything is inputs, apart from kind of the final result of the program. So what you have here is you have the input, which is the two values you want to add together, and then a third input, which is the rest of the program. So what the value, as you think of it, would flow backwards down this arrow, but what's actually happening is the rest of the program is being passed as an argument. You deal with these with promises and result maps and so on and so forth. And yeah, this resource, which I'll link to my slides at some point, this is a really good way of kind of just describing continuations or diving into continuations. So what we have here is we have programs perform effects with the remaining program captured as a continuation. So I've shown you the perform keyword. So what you end up with here is you end up with this pure program, which says, okay, the perform keyword takes a label, it takes an initial value, and it takes the rest of the program, which we call resume. There's no range, so the value we pass in is just the empty record, the label is random, but then resume is very specific to the program. So resume, after we've got a random number here, is going to be the rest of the program. And in many ways, this is where your program stops. This was the result of the calculation. And you pass this to the outside world, the scary place with the missiles. Okay, and so some point later, the outside world goes, I know the answer. I know an answer. I'm going to call the resume with the result I want to call it with, and we'll continue with the program. So the rest of the program was just to add 1. So if random was to return a 4, we return 5. If random was to return 10, we get 11. But the interesting thing is the entire rest of the program just becomes a value that you can hold on to, and you can put on disk. You could run 4 to 5, immediately, and you could run this thousands of years later because you can serialize the program. So this is kind of my, I guess, sleight of hand to say that EYG programs never crash. Because a program is deterministic in the absence of any effects, and EYG programs are serializable. Okay, so they can be put back to disk at any point, and the continuations after asking for an effect to be formed can also be put on disk. So a serialized continuation can always be run on another computer. So if anything interrupts your program, you can always restart it with the inputs that you gave it. And okay, you might argue, well, what if I lose those inputs? Well, because the continuation can be run at any time, you don't have to run it straight away. So if you were to run the program and it was to say perform a random effect, and you never want to lose the state of the program, you globally distribute it saying this was the result. And when we've all got a copy, we go, now we can run the rest of the program. So in my argument, computers can crash, but programs don't crash, or programs shouldn't crash. And anyway, that's my sort of sleight of hand argument, and that's kind of the crux of that. But there's a few more things that I want to kind of, I've said about EYG and why it's valuable and where fragility comes from. I'm going to take a little kind of next section into structural typing. So what are the benefits of a type system? So again, LambdaConf, I think we've got a lot of strongly typed functional languages. We don't want runtime exceptions. We want our type system to tell us there's no mistakes here for the class of mistakes that it can catch. Okay. But I also want to go, well, what's the benefits of a type system in this program? So this program prints hello world. I don't think anyone was told that, the type signature of this print statement the first time they programmed, because you don't need it. And why don't you need it? Like, why is it not useful? Why is this incredibly useful and it's not useful? And it's because it comes down to scale. Like, we understand this program. This program has far less logic in it than it has interaction with the outside world. And so I think that, a type system is based on its size, like the value. So the type system, you have some consistency guaranteed based on some axioms. So this might be your FFI bindings. So, if you use a library, a JavaScript library in TypeScript, you have to declare what the types are. If you get that wrong, then the compiler doesn't help you. The compiler assumes that you get that perimeter specification correct. But if you specify that perimeter, it guarantees that within the context of the TypeScript program, everything will be good. So the axioms are the perimeter, and the wider the perimeter for our axioms, the more valuable the type system. All right. So web development. So here we have backend and front end. So we've got lovely languages on the back end. I don't know what we're. We've got some F#, we've got some Gleam, we've got some EYG. They are, strongly typed. It's consistent. This back end is never going to crash. The front end, we're using Elm. It's also never going to crash. But we have to manually wire up everything in between. So these APIs, they're all to some degree untyped, or they are typed, but they're not normally part of our compiler's type system. Is probably the best way to say it. We've made some progress in this direction. So meta frameworks, they do some amount of tricks to treat your backend and your front end as one entity. So you have one program with one type analysis step. Runs over a code that will run on multiple computers. And web development is far more than the front end and the back end. So I think this work with meta frameworks is really nice, but it's kind of limited in that we've just made, we've got one system for front and back end, but we've got lots more places where code runs. One of my personal pet peeves is service workers. You have to, if you haven't done the web development, a service worker is always another JavaScript file. You can't start a service worker. You can start a service worker in the browser, but the code has to come from the server and be defined ahead of time. And you have another stringly typed interface between the two of them. So the question is, how often do we statically check the glue? And why don't we? So here's my hypothetical picture, and this is all possible with EYG, and we'll get on with this a bit. On my developer laptop, I run something, and I return a function. It's just a continuation. But I want to ship that continuation to the build server. So a continuation that goes to the build server just has to have a type that it takes, say, maybe the time that it was performed at. This function can have effects, and those effects can be constrained to what the build server has available. So it can read configuration, it can read the file system, then there's some assets that are available. Okay, on the build server, that returns another continuation. This continuation takes a request because it's going to a web server. So again, we ship this continuation off, this continuation takes a request. The application server has its own set of effects, for example, access to the database. And it, when a client comes along, sends off another continuation. So this goes to the browser. So here we have the kind of the tiniest program that works like this. So we have just a 3-argument function where it expects that each argument is applied to this function on a different computer. So everything's curried. So we have systems. So the return value of system is something that takes config. These can all be ignored. But if I call this, and the annoying thing is going to, the type system knows that there's 3 arguments. But anyway, if we call it with one thing, oops, click here. What we get is we get a function that takes a request. This in EYG can be serialized. We can move on. This is great. Call it with another one. Pass something again. That doesn't matter. We're going to get something which accepts a client. So I've said a client, not window in this case. Right. So closure serialization is the magic that's going on here. So, okay, closure serialization. I've kind of just dropped that in as a term which is, useful. Closure serialization is the idea that you can take a closure, which is a function and some environment, and put it back into source code or back into something the program can access. So here we have this capture built in, which is available in EYG, and we take this f, which is a function here, which uses amount from the environment, but it doesn't use message. So if we capture this, this is a flat representation of the AST of a EYG program. So I won't expect you to read that as we go along here. But one of the interesting things we can do is we have another built-in, which is called serialize. So serialize takes that AST and puts it in a JSON form. So here we have a lot of JSON. Again, why you can't necessarily see that this is the function f, but for example, if we copy this and we go up here and we put in another variable, which we're going to call temp. Okay, how do I exit that? Bear with. Maybe if we just refresh the page. Oh no. What did I do? Blah blah. Reducing. Oh, I think you get rid of the P. Yes. Okay. I wonder which one I think there's a keyboard shortcut that I've picked up here, which I don't know which one it is. So that's highly risky. Okay, J, serialize. We're going to copy this. We are going to put something in the line above, just underscore, it's not that. Right, so if I paste this, okay, ooh, mystery in these brackets. Go in here. Yeah, we have got the function that we wanted, function f, with just the environment that we needed pulled in. Great, cool. So let's move on to another example. So closure serialization, here I just showed you what it was, but I want this use case, okay, this developer laptop approach as we go along. So let's go full screen again, this should work. Actually, we're going to have to shrink it again almost immediately, but never mind. So we have this app that we want to deploy. So first things we want is we want to turn this into a script. So if we say, oops. I did want to show you we have JS generation. It's magic. If we have time, we'll come back to it. So script. Oh, no, you picked up new ones. Equals script. I went through this one before anyway. So we have a built-in, which is called to JavaScript. We call this. We're going to pass in the app. I think we just lost focus somehow. It's very frustrating. I'll just have to keep clicking. Right. So this is the script. From the script, we want to make an element. So we're going to say element. I keep losing the focus. Element. Right. V string get. Yeah, this is very frustrating. So C does that. Right. If this keeps happening, we will move on quicker. But I think we can hold this together. So we want a list. We want a list of 3 things. This needs to be script tag. This needs to be the variable script. No, don't press C, that's the key one. And then this needs to be the string, click in here, which is a closing script tag. Right. We come over down here, we want to download this. So we want to equals content. We're getting closer. Binary. Again, not binary. We would like to turn string into a binary. We would like to call that with the element. Right. So if we crack on with this, so the program is to alert hello. So we want to do the effect. Okay, closer. Click. download, click the name. The name is going to be app, focus, app.html. The content is going to be the content. Okay, so now we need to run this effect. So if we run this effect, we download. So we need to shrink the screen again. Maybe we shouldn't go full screen. Here we have app.html. If we run app.html, we alert with hello. Okay, so this is using the environment. So the app is in scope to pass to something which has a JavaScript. We can constrain this. This is a continuation sent over the wire to make the deployment pipeline. Hello world. Well, let's say hello Lambda. Hooray. Conf. There we go. Yes. We click to run this. We get another version. We run it. Hello LambdaConf. Great deployment. Okay. So a thought experiment. Like imagine a perfect language. Okay. The language you want. You can get your mum to write it. Perfect language. But libc is not installed. You've got to call an undocumented JSON API. You need to implement OAuth, and the whole pipeline is Bash. Well, you're not going to have a perfect experience, even if you get to use your perfect language. And so I think like this glue stuff, and a lot of it is this kind of untyped world we have around it. So one of my pet peeves is kind of the pipes. Unix pipes are untyped. You pass out string. String is the one true format, text. But if you break your program down a lot, you end up in an untyped system. The file system is essentially a string-to-string key value store. Again, perfectly nice, simple abstraction, but it means that it's untyped. And then we have Kubernetes. So this is what I think of, Kubernetes does to your type system, right? The more you shrink this, the more you have microservices, the less you have type. Like YAML, another stringly typed system. I mean, even if you kind of do analysis over your YAML, which is sort of possible, it does not tie into the language that you're using. So can we type check the whole system? Like this is the kind of question. And the answer is yes, right? I worked out to my satisfaction how I do this. So one of the key things that we have to do this is we have to use structural typing. And so this is quite a kind of like probably the most subtle point is structural types are universal and nominal types are not. And what I mean by this is when you name something in a nominal type system, when you make a user type, all the functions that can take that user type come from the same compilation artifact. They come from the time that you ran it over. If two people wrote two systems at two separate times and they define a user type, there's no authority which says which one has the correct user type. And the only way you can check if they're the same is to start coming back and going, well, are they structurally the same? But if you were very carefully to create an email type in one project and a telephone type in another project, and they both aliased back to strings, well, the comparison would say that they were the same type. Okay, so nominal typings have a bounded validity, whereas structural types they're at least universal to the language. Like if you use different versions of the language, you might get a different result. But taking one language system, structural types are universal in that. And the other thing about nominal types is they require someone to do the work to actually define them before you can use them. Whereas structural types kind of all exist at all times. So, okay, this is me just saying the same thing. Part of the fact that maybe they look very similar. So here, Java, you've declared a person thing. There's no way to create a person object unless it's a person object. In TypeScript, the interface is just enable given to anything that's got a name field of string, and you can pass other things in as persons. So this brings to like the fun party trick, which is, well, okay, we've increased our typing, we've got our meta framework. What about if we deploy a new system? So the system at time 2 is never available when we type check the system at time 1. Can we type check across this? And the answer is yes. So how much time have we got? I've seen a 10-minute check. I think, yeah, we'll do this one. So if we switch over here, this is the EYG homepage. I will make this, I think, slightly larger for everyone. So I've not managed to work out how to get this example into slides, which is the only reason we're over here. This is the EYG.run homepage, so you can use this. So here we have a little front-end app where we have an environment where if you return a render handle init object, we make a little app. So here we have the app. And the app state Oh, no. Oh, we click this one. So yes, the render function says the total is the count. And clicking on it calls the handle function. So every time we click, we increase by 1. Now we can edit this program as we go along. So we can make this number 10. And if we scroll down, this is automatically deployed. We've kept the app state, the total is 16, but now we increase by 10 each time. Now, if we go along and we're like, okay, we need a slightly different state. If we make this a record with a count field, okay, we go down here, we get an error, a type mismatch. Okay, so the type mismatch is in a few places. Obviously, the handle function is just trying to add to the state, so that doesn't work. We need to get here the count field, and we need to return an object which is in a count field. So we put this in a count. Okay. We're going to get the same error. Okay. We come down here. The render function is dealing with the old state. So if we press R to destructure that, our init, handle, and render function now all deal with records with a count. But if we come down here, we still have an error. And the error is that we're missing the row migrate. So the error messages are not super up to date, but this is the migrate field needs to be on this record at the bottom. So if we come down here, we decide to add another item. That item is migrate. We go in here, we make it a function. So press F. So we have old. If we just, I'm still using the focus. If we just have a function from old to old, we've not migrated it well. And we get back to the type error. No, we needed this expectation. So if we migrate old to something which has got a record field of count, we go down. Right, the type system knows it's good, but upgrading is a destructive action. So if we click to upgrade here, we now get the app state upgrade. We keep 46. We keep our upgrade function. So this is working by structurally typing the old and the new version of the program and having enough rules around that you can do the migrate in between. So there you go. That's kind of a demonstration by existence that is possible. So I think that means we've got just a couple of minutes. This was something I put in like about the writing, about what EYG is. Deterministic dependencies. Every dependency has an inline checksum. That's pretty much the entire trick. Every dependency is pure and its type is narrowed, with meaning that functions can only have effects like once they're called in the program they run on. Maybe that's not the clearest way to put that. I'll think about that one a bit more. But yeah, so I showed earlier here that we have, we can pull in string. If I press @ we get the named references that are around. Okay, so this is this means my internet's gone down, or at least lower. Come on, let me have this. We will try one more. Give me the libraries. Standard. Undefined standard. Well, we won't dive into that right now. Well, I suppose I can demonstrate one bit. This, if assuming this had loaded, we can copy this. Caps lock. Is that what we've done? No. Caps lock on, caps lock off. Copy this. Y. Interesting. Well, this being a structural editor means it doesn't have to present on screen exactly what its the underlying structure is. So this AST node has a checksum embedded in it. And the thing I was trying to show you was if I copy it, but for some reason that's gone round to paste. So, I mean, maybe I can just try and do the other one. We'll give it a go. We then paste in here. V. No, that's the whole previous program. Right, one more refresh. Come on. Something's taken over this tab. Standard. Release undefined standard. All right, now it's loaded. Try and yank it. Go to the string. Oh, not doing it. Okay, we'll have to move on. So eat your greens. Eat your greens is the idea of, yeah, kind of eating your vegetables. And so we have a really simple type system. So the records, the unions, and the effects are all implemented with the same row type implementation. So the type system is very small. And I think it's more interesting to try and put this simple type system everywhere than a complex type system. I want to extend the type system over time with migrations over the front and the back, and also over the build to applicate, like to CI, to server, to client, to service worker as one system. That's the goal with EYG. Okay, run anywhere. Wow, I just threw this in as a thing we can do. Okay, if you have the effects, I mean, the shell's been running in the browser where we had a download effect. You can run an EYG program as an app script. You just have to specify a runner that has the effects of the app script platform. The same works for Figma plugins. The same works for something like TinyGo. So I have run EYG on an Arduino. I just implemented the LED effect. It was an effect which took true false to turn the LED on off and returned unit. Didn't tell you whether it succeeded or not. It was just it did that. Making a runner for something that simple was very easy. And so putting a platform for an EYG program on an Arduino was not a large job. Anyway, I think that wraps me up. So thank you. It's nice to talk to you. If you want to find out more about this, the website is eyg.run. I'm currently in the process of releasing a bunch of things at 1.0, which means I've broken them along the way. So the AST format, the hashing format, the standard library, they are all fixed to a 1.0 release. But the actual platform effects that you will find in the shell on that website will change over time. And if you want to keep up to speed with that, there's the EYG news where I do kind of ad hoc newsletters on what's going on. And then there's a roadmap which explains all the things I think I need to do to get to a stable version where I will be happy guaranteeing that your code will run into the future. So yeah, thanks for listening. And if you have any questions, please drop them in the chat or somewhere else that I can find them.
All right, thank you very much, Peter. So I will just say, we don't have too much time for questions, but there's been a number of talks at LambdaConf this year concerning orthogonal persistence, determinacy, and the ability to transfer code across platforms, which your project is very much in line with. So I'd encourage you to post this in the Discord because you should attract some attention there as well.
Right, okay, thank you.
Otherwise, thank you for your talk, and we'll see you next time.